What is entropy?
Entropy is a deep concept and it doesn't have a single universal definition. In fact, trying to reduce it to just one idea can lead to confusion. According to physics, thermodynamics, statistics, and even philosophy and biology, entropy can be understood in different ways. But they all have one thing in common. Entropy is a natural tendency of energy to spread out. It's the measure of many possible states a system can take. It's the amount of heat that gets dispersed when a system changes state. I explain all of this in a clear way using simple and technical examples, and I will show you how this concept relates to engines, the human mind, and even the fate of the universe. Imagine you drop a cup on the floor. It shattered into pieces, but you never see the pieces coming back together on their own. That is entropy, the natural transition from an ordered state to a more disordered one. Why don't perpetual motion machines exist? Because in a closed system, usable energy always decreases. It doesn't disappear, but it turns into forms we can't use anymore, like scattered heat. That is entropy, the part of energy that can no longer do useful work. A simple example. You put a hot spoon in a glass of cool water. The heat from the spoon spreads out the water. In the end, everything reaches the same average temperature. The thermal balance happens because energy has been dispersed, entropy increased. Let's say I take a scrambled Rubik's Cube, close my eyes, and start turning it randomly, without thinking. I keep moving and turning it to pieces for 5 minutes straight. Will you bet that the cube ended up solved? Or would you bet it's still crumbled? Exactly, it's scrambled. But how do we know that so quickly? Because there is only one microstate where the cube is perfectly solved. Yes, it's possible that, by chance, I opened my eyes and the cube was solved. But there are 43 quintillion other microstates where the cube is still scrambled. The exact number is this, and only one of all those combinations shows a solved cube. Entropy tells us how many different ways a system can be arranged inside. The more possible configurations, the more likely they are to happen. That's why entropy always tends to increase. Because the most probable outcome always wins. In this case, the scrambled cube. But it doesn't stop there. That's just a cube. Let's ask something else. Why doesn't an ice cube heat up my coffee? To answer that, we need to look at the quantum level. The ice cube is made of trillions and trillions of particles, and so is the coffee. For the ice to heat up the coffee, an extremely rare scenario will have to occur. Something so unlikely is more probable you'd win the lottery 10 times in a row. A solid ice cube has fewer microstates, but when it melts into water, there are billions more microstates. The liquid state is way more probable, so the ice melts on its own. What about gas in a box? It never stays in one corner, it spread out everywhere. Why? Because there are way more possible microstates where the particles are spread out than when they are all concentrated. Entropy always favors disorder because, statistically, disorder is what's most likely. Entropy also measures how much heat can be into useful work. For example, imagine two metal blocks. One at minus 100 degrees Celsius and the other at 100 degrees Celsius. Now imagine I told you the cold block could transfer heat to the hot one. Yes, technically that's possible. But why doesn't it happen? Why doesn't an ice cube heat up my coffee? Because, as the second law of thermodynamics says, heat naturally flows from the hotter object to the colder one, not the other way around. To reverse the flow, we need external work, like a motor, a refrigerator, or a compressor. If there is no external intervention, energy spreads out, and entropy increases. In any engine, not all the energy becomes movement. There are always losses. Due to friction, electrical resistance, or mechanical drag, that lost energy turns into heat. It doesn't vanish, it is spread into the environment. And as that reading is exactly an increase in entropy. Entropy measures how much usable energy is lost at heat and how many different ways that energy can be distributed. The more it spreads out, the more entropy there is. That's why no engine can ever be 100% efficient. Can we beat entropy? No, but we can reduce it. Understanding entropy helps us build more efficient engines by reducing friction, improving materials, cooling the system in smart ways. This way, less energy is wasted, and the engine lasts longer. Entropy is used to describe mental complexity or disorder. A brain with low entropy may be too rigid or inflexible. A brain with too much entropy can become chaotic or out of control. Balance is the key for healthy brain function. In biology, every living organism is constantly fighting entropy. To stay alive, it consumes energy and uses it to create order, maintaining cells, repairing tissues, organizing functions. But in doing so, it releases heat and waste, increasing entropy in the environment. Life is temporarily sustained order in a universe that tends toward chaos. Entropy is connected to the final fate of the universe. As time passes, usable energy fades, heat spreads out, the universe becomes more uniform and less structured. This leads to the idea of the heat death of the universe, where everything reaches thermal equilibrium and nothing new can ever happen again. Entropy is not just a measure of disorder, it's a universal law that cuts across every discipline. In physics, it explains why things cool down, break, or scatter. In engineering, it makes the design more efficiently. In biology, it explains how life fights against chaos. In philosophy, it explains why the universe ages. In psychology, it helps us understand the complexity of dogs. Entropy is the language of time, change, and the inevitable. Thanks for watching.